definition we're going to work with here is n choose k is equal to the number of subsets of the set 1, 2, up to n that have cardinality equal to k. And equivalently, another way you could place this definition is you could say, or it's the number of ways to select k objects from a set of n objects. And we're assuming that when we select them, we have to pull them out and you can't reuse any of the objects for multiple spots. And the formula for this is we're going to have n factorial over n minus k factorial on top. And this is the number of ways to take k objects in order. And we're going to be dividing it by the number of ways to rearrange k objects. And then what people usually do is combine these using fraction division. So you'll more commonly see this written as n factorial over n minus k factorial times k factorial. What would 0, this is called choose, this is called n choose k. What would 0 choose 1 be? A set with 0 elements. How many of those subsets of that set have 1 element? 0. What about 0 choose 0? It would be 1. Why? Another way to think about that is this is the empty set, and there's one subset of the empty set that's empty, which is equivalent because they're different ways of thinking about the same thing. So when you select a set and the order doesn't matter, you're doing a selection, and you can do this formula or any of the equivalent formulas. If you're actually trying to code this up, this way is much slower. Think about it, you're doing all these multiplications on top just to cancel them. So from a computational perspective, it makes a lot more sense. Just do the product notation because you don't do all these multiplications that you're not going to use. In arrangements, I think we found, we felt good about arrangements last time. So if we're taking k books out of 8 to give to k different friends, how many different ways can we? This time we did 3 books and we were giving to 3 different friends, and y'all told me the answer was 8 times 7 times 6 because you were using slots, idea, product principle, whatever you want to call it. And so now we're going to try to generalize this and say, if we have this generalization from 3 to k, and we're taking k books out of 8 to give, how many different ways can we do this? So what would the process be to do this? I'm going to have 8 choices for the first book, 7 choices for the second. I'm going to keep multiplying down, and then I'm going to stop at 8 minus k plus 1. And the temptation is to think that you're going to stop at 8 minus k. But if you look at an actual example where you calculated it, we didn't stop at 8 minus 3, we stopped at 8 minus 2, because we actually started at 8 minus 0 times 8 minus 1 times 8 minus 2. And so we're not going, when we're subtracting off, we're not going from 1 to k, we're going from 0 to k minus 1. When you write it out in products notation, it does become from q equals k. This would be from q equals 0. One way you could write this would be q equals 0 to k minus 1. And the things we're going to be multiplying together are 8 minus. Every time we come here, we subtract something. First, we're subtracting 0. Then we're subtracting 1. Then we're subtracting 2. And we're multiplying all those together. That's one way you can write it. The way you'll more commonly see arrangements written is using this factorial notation. Usually the formula for an arrangement will be n factorial over n minus k factorial. So it's exactly the same as the selection formula that we developed here, but there's no k factorial for rearrangement. So formula-wise, the difference is just whether there's this k factorial on the bottom, although there are other ways to write the expressions with product notation that are good to know.